Bir dakika. Yok, beni duyanız mı?
Telefonu kapatayım da oradan götüreyim.
Aha.
Sesini
Beni duyanız mı?
Sesim geliyor mu hocam? Sesim geliyor mu?
Sizinki geliyor.
Ben kapatıyorum sizin
Sesim geliyor mu? So I hope you listen me. So title of my
our first plenary speaker, invited speaker, Professor Dr. Allaberen from Bahçeşehir University, Istanbul, will give his talk. Here you are, Professor Allaberen.
So my greeting for everyone. The title of my talk, the kernel identification problem for the parabolic integral differential equations. Joint collaborator, Professor Durdumohamed Durdiyev from Bukhara State University, Istanbul, Uzbekistan. So this paper investigated the kernel identification problem in a Banach space for parabolic class, specific class of parabolic integral differential equation. The main theorem on the existence uniqueness of bounded solution for the kernel identification problem is proved. Especially, it shows that there is a exists a unique solution, boundary solution identification problem given the data. The paper extended these results to 4 types of kernel identification problems for parabolic integral differential equation. For each type, we prove the existence uniqueness bounded solution, which suggests that methods developed are quite versatile and applicable to various forms of parabolic integral differential equation. By providing results for type of identification problems, the paper demonstrates that the framework can be handle a broad range of practical scenarios where integral differential equation may be not with dependent coefficients. This is practically relevant in the real-world applications, where is relations between the terms of integral differential equation can be complex. Outline of my talk: first, introduction and formulation theorem; second, auxiliary results; third, main theorem, existence uniqueness bounded solution of the kernel identification problem. Second, applications main theorem for two different problems, and conclusion and our future plans. Identification problems for the partial differential equation arise in all perspectives in the design of optical device, geophysics, and in the several other areas where the interior of the object is to be imaged using the response of the acoustic waves. Identification problems of memory kernels in PDEs have been intensively investigated by many researchers. Here I consider here 6 authors from different countries. The evaluation convolution integral differential equation have been investigated also with many people, but I consider here last papers. Identification problems for determining the kernel of the integral convolution term, specific type of integral differential equation with constant coefficients have been investigated by many researchers. However, such type identification problem for determining the kernel of the integral convolution term for parabolic type integral differential equation with dependent coefficients and with classical and non-classical boundary conditions have not been well studied before. The main idea in this paper, we will consider kernel identification problem, parabolic equation, parabolic integral differential equation, like one in Banach space with unbounded operator. Here, as you see, first left side term parabolic, right side we have nonlinear term, convolution term. There is two unknown function, kernel function unknown, also psi unknown. A is a strong positive unbounded linear operator with denser domain in the Banach space B. Mu element of domain of A. P is a bounded linear functional on B. F is a smooth, given smooth function on the interval 0 epsilon, of epsilon. Psi of t is the unknown abstract function defined on this segment with valid arbitrary Banach space B. K is the kernel function that needs to be identified. So the main theorem on the existence uniqueness bounded solution of kernel problem for parabolic integral differential equation 1 is proved. In practice, theorem is on the existence uniqueness bounded solution of the bound for the 4 type of kernel identification problem for parabolic type integral differential equation with dependent coefficients and with classical and non-classical boundary conditions as are proved. So we introduce here psi of t and k of t functions by acceptance formulas. So this is a really operator functions of k of t, all one dependent here, mu phi of t. A pair of function psi of t, k of t is considered the solution to problem 1 if it is satisfied the subsequent conditions. First, abstract and scalar function psi of t, k of t are continuously differentiable on a given interval. The element psi of t belongs to domain of A for all t, and the function a phi of t continues on this closest segment. A pair of the function psi of t, k of t satisfies both the parabolic integral differential equation and initial and kernel identified condition given in 1. The solution psi of t, k of t of the kernel identification problem for parabolic integral differential equation 1 defined in this manner will be from now on the referred to us as the solution identification problem 1 in the spaces CB, C0, epsilon. Here, CB is the space of B-valid continuous function psi on the interval occupied with the subsequent norm defined by 2. Let us introduce some auxiliary statements will be necessary for the subsequent sections. First, we will define a positive operator with spectral angle. The operator is said positive if its spectrum sigma A lies on the interior of the sector angle phi symmetric with respect to the real axis, and if on the edges on the sector S1, S2 and outside it is resolvent, is subject so bounded. So satisfied estimate 3 on the S1, S2 and outside. The infimum of such type angles phi is called spectral angle of positive operator and define it like that. Operator is say strongly positive Banach space if spectral angle less than of pi over 2. Let the operator A strongly positive. Then the operator minus A generate analytic semigroups for positive t and exponentially decreasing norm when t approaches to infinite. This behavior is reflected in the following estimates for here some constants m we present a convenient new form parabolic identification integral differential equation in problem 1. So theorem lemma 2 let k of t continues to differentiable function. Then the parabolic identification parabolic integral differential equation in problem 1 is equivalent to the parabolic integral differential equation 5. I would like to draw attention here. We will here consider equivalent form, convenient new form 5. So here some proof about it, but it is based on the classical theory of differential equation. So I will consider here theorem lemma 2. The kernel identification problem for integral differential equation 1 is equivalent to the following auxiliary kernel identification problem for the integral differential equation like 13, 13 and 15. So now, as you see, we have here 13 parabolic problem, a parabolic equation, and also two conditions, initial and here identified conditions. We will denote it here phi of t, a psi second order derivative, and we denoted also k of t here n prime of t. So we define it here new unknown functions. So here we will prove equivalency theorem, or it is follows also introducing new functions phi1, phi2, and we define it here some auxiliary solution, and we will prove statement equivalence to these problems about these problems. Neyse, now next we will reduce the Cornell identification problem for integral differential equation 1315. So all now investigation based on the investigation of identification problem 1315 to the system nonlinear Voltaire integral differential equation in the sequel to which will be applied fixed point theorem. So all this preparation about how we will apply it fixed point theorem. Now using results of paper, we can write equivalent form, integral form 23 from our problem, and we obtain formula for v of t and k of t, two unknown functions. Adding the operator p to the equation 20 and taking the into account 21, after simple computation, we get formula h of t by 24. For applying fixed point theorem, we rewrite integral differential equation 20 and 24 as an operator equations. Xi equal phi of xi. Here xi of t a vector function, abstract function, and is this a symbol of transposition above here, symbol transposition, and in accordance with the equation 20 and 13. The operator f has form f consists vector like vector of a function f1, f2. Formula f1 defined by 26, and formula f2 defined by 23. Here we define it xi01, xi02 such that follows from given data. And we denoted here xi0, also vector with coordinates xi01, xi02. So, and now we will consider some spaces where it will work. Let us denote by C gamma Banach space of continuous vector function, xi of t vector functions, with values in abstract Banach space on the given segment with weight norms. Xi gamma defined maximum norm of coordinate functions, but now here it is defined by exponential minus gamma y, as you see, as product. It is obvious then if we put Xi0, the space Xi0b coincides with the spaces CB we introduced before. So from inequality, it is follows the norm Xi gamma and Xi equivalent for any fixed gamma, and let Xi rho is a ball of radius rho with center at the point A of the space C gamma. So we define it by 31 ball. In this ball, we will consider application of fixed point theorem. Here, rho some arbitrary number, we will define it, choosing more later. The convolution operator is commutative and invariant with respect to multiplication by exponential minus gamma t. So very easy to see 32 and 33 are satisfied. Therefore, last formula implies the estimate 34, and using 35 we get 36. This is a really important estimate for application of fixed point later. So now main theorem on the existence uniqueness bounded solution of Cornell identification problem 1. Now we are ready to formulate and prove theorem existence uniqueness bounded solution of Cornell identification problem, which is our main results. Theorem 3.1. Suppose phi of t smooth, that means there is continuously third order derivative, and mu from domain of A cube, the matching condition F0 equal pair of mu, and matching condition prima 0 equal minus pair A mu, and the inequality pair A mu different from 0 are valid. Then there is exist and unique bounded solution of the problem 1 in the ball sigma rho Xi 0 at the center Xi 0. So proof, at the beginning we proved the operator A19 has a unique bounded solution. So show that operator F is contraction mapping operator on the ball. If the sigma or gamma chosen in a priori way, here gamma must be. We recall that operator F is called contraction mapping operator in ball if satisfied two conditions. You know about it. So really we will prove these two statements. About first proof, first property, if Xi element of this ball must be phi Xi also from this ball. So we will prove 1. Let Xi from this ball, then inequality 20 follows 38. This estimate 34, 38, 5, and triangular inequality we will estimate for norm of first coordinates. So such type estimate, as you see from that, if it is above that, if we choose gamma as 39, greater than equal gamma 1 and gamma 1 defined by this formula, then first norm of first coordinate less than rho. Similar way, we will obtain also estimate for norm of second coordinates. So also some with some big number, and now it is above that. If we choose gamma now greater than gamma 2 defined by formula for t, then norm of second coordinate also, so that means our now vector phi c from this ball. So now first one proves, we will try also prove second one. We take C1, C2 and arbitrary elements, and first we will give estimate for first coordinates. As you see, also we have formula 31, and so now this first norm, a second norm also similarly, and now we have estimate if we choose gamma greater than gamma 3, here maximum, here we will write number taken by 31 first, this is second one. So, and choosing such type, we will get also a second condition. Therefore, if the choose gamma as big than gamma 1, gamma 2, gamma 3, then at any epsilon, the operator F satisfies the both property contraction mapping operator. F realizes contracted mapping on the ball, onto itself. So then according to the Banach theorem, we have exist and uniqueness solution, and we can also give formula for solution such that follows directly from fixed point theorem. And after that, we will find all unknown function, because all unknown function we can find from now finding of solution of new problem. So now we will consider here application of main theorem. Now we explore the application theorem 1 on Cornell identification problem for parabolic type integral differential equation. First, we begin addressing the Cornell identification problem 33 with no local condition with respect to second variables. And here, functional defined by last formula. It is one dimensional parabolic Cornell identification problem for integral differential equation, parabolic integral differential equation. And delta sufficient large number and alpha of y, mu y, f of t given smooth functions and satisfied compatibility condition ensure that problem for t the smooth solutions vt y and k of t, and we will assume that alpha y positive and satisfied here periodicity conditions. So how many time I have? So let us our given data smooth and satisfied matching condition 40 and inequality 35, then there exists unique solution problem 30 in the ball 36. And the proof of theorem 31 relies on theorem 31 as well as the strong positive C1 differential operator defined by formula 37 with corresponding domain and boundness C01 linear functional pair defined by formula 38. Okay, second example, a special type of functional parabolic problem, integral also plus. Here we have involution. So we consider here kernel identification problem for one-dimensional parabolic integral differential equation with involution with respect to y. So here we also give some smooth condition and compatibility condition for exact solution, and we will give some condition 58 for coefficients of differential operator, and under the condition 31 and 32 we have existence uniqueness on this ball and proof it is based on the abstract theorem and self-adjointness and positivity L2 differential operator defined by formula, and also boundness in L2 linear functional defined by formula 55. And third, we will consider unit open and dimensional Euclidean space and boundaries defined like that. Let S denote the boundary and kappa union Q and S, we consider the kernel identification problem. First is multidimensional parabolic integral differential equation. So similar theorem we have also for this problem. Here only one more about multidimensional case. We need sharp estimate for the solution elliptic problem. And last problem also multidimensional, first with Dirichlet condition, here with Neyman conditions for kernel identification problem, multidimensional parabolic integral differential equation. And so similarly proof like before for the Dirichlet case, and next last chapter about our conclusion. In this paper, the kernel identification problem for parabolic integral differential equation in a Banach space Ben şu an toplantıdayım da So first part about our results, and second about our plans. But we consider here one new concept about existence uniqueness of parabolic Cornell identification problem, parabolic integral differential equation in Banach space with applications. And next, our idea, construction investigation, single step, absolutely stable difference schemes for numerical solution, Cornell identification problem for parabolic integral differential equations. But really, for parabolic equation, such type high order accuracy difference schemes constructed by many sciences. You can find in our monograph all many statements here. But of course, the convergent estimate solution of these difference schemes can be obtained also. Third problem, some Cornell identification for parabolic functional integral differential equation will be investigated along the real life applications. Here, the basic, we will consider Vlasova monographia. It is more useful, but really in my talk, second example about such type problems, but it is starting point we will consider more later. So I would like to invite also our conference, which will be held 23-28 September, organized by Bahçeşehir University and Center Chent University, Belgium and Kazakhstan. And to submit your research paper in our journal, electronic journal Analyze Applied Mathematics. And also, I invite our weekly online seminar organized by Bahçeşehir University, same with Ghent and Kazakhstan. Thank you very much for your attendance.
Thank you for your talk, Professor Allaberen. Is there any question to Professor Allaberen? Thank you very much.
Thank you very much.
Thank you. I think only 5 minutes we have, 7 minutes we have for the next talk. Kojin accent.
Professor Chakali, hello.
Hello.
Kochinas is speaking.
Hello, Professor Kojinak.
How I can upload my file?
Yes, I am doing that thing.
You will do that instead of me?
Yes.
Yes, okay, thank you.
I will do for you.
Can I try to upload? If you have some
instructions. You can upload your either upload or share your screen.
Okay, let me try to upload by myself. Can you help me how to do this?
Okay. Oradan çıkacağız yani. Şimdi ben de yüklemeye çalışayım da ihtimale karşı. Şimdi şöyle.
Hocam ne kadar ara var?
5 dakika, 5 minutes. 6 minutes. 5 minutes left, yeah. Professor Kojand, I uploaded for you. If you can use either my uploaded
Okay,
file
okay.
or
You
can
help me
you can share.
how to share?
Yes, okay.
How I can
If you
upload? Can you help me how to
yeah,
upload
you can upload.
Yes, if no, I'll
Okay.
use your.
5 minutes break, coffee break, tea coffee break. You can have your tea coffee.
Okay.
Okay. See you. See you 5 minutes later.
See you.